Alright, so welcome back. This is going to be a pretty short video. I want to talk about what are called assembler directives. When we write our assembly language program, we say things like increment F 0x20 to increment file register 20, or move WF 0xF80, because we know that F80 is the file register number of port A, and we want to send something to port A or read something from port A. But we don't want to really embed these magic numbers like F80 into our program. Number one, because it makes things more error prone, and number two, because it makes it harder to read a program. So I want to talk about some things you can do in your program that don't directly generate code but control the process of assembling your program. So one thing is putting in lots of comments, right? This block up here is a comment block. It doesn't have any effect on the generated code, but it says what the file is, a description of it, the date, and so on and so forth. Another thing is this RADIX hex. When you say RADIX hex, it means that from that point forward, if you have a number like 10, it means 10 hex, which is decimal 16. If you say RADIX dec, which means decimal, and you say 10 somewhere, it'll mean the decimal number 10, right, which would be the hex number A. So if we don't want to constantly say 0x7f, we can say RADIX hex and then just say 7f. But it's good practice to put 0x in front of hex, again, because it makes things more readable. But you may see things like RADIX. This config statement is something that we always need to put in the beginning of our program. Config wdt equals off, lvp equals off, osc equals int io2. And this is just something that we always put into our code. And we'll talk about what that means later, what each of these three pieces actually does. But for now, just always put this line in the beginning of your code. So I want to talk about some other examples that are good to know. So one is the statement org. So we can say org, and then we can name a location in program memory. And typically, we'll say org 0x00. What this statement means is that the next instruction that we write should be stored at location 0. And then the next instruction after that should be stored 2 locations later, instruction 2, and so on and so forth. This is what we've been assuming happens. When you start the PIC processor, it starts executing code from instruction 0. But if we said something like org 0x20, and then we say increment file, something, this instruction is not stored at location 0, it's actually stored at location 20 in the program memory. And then the next instruction would be stored at 22, and so on. So if we want to put instructions into our program memory at different locations, we can use this origin statement to say where instructions should be stored. So that's going to be useful. All right. Another useful instruction is EQU. And in our program, we can say something like, we can pick some variable name like x, and we can say EQU, and we can put some value over here like 0x20. And this means that the symbol x is basically a synonym for 0x20. So when we're using temporary variables, if we've got a count that we're using to keep track of how many times a button has been pressed, we would want to decide where in memory are we going to store a count, and maybe we're going to store a count at location hex 10. So every time we want to increment our count, we would say something like increment file register hex 10. When you're reading your code, what does this mean? Why am I incrementing file register 10? So what we would do in the beginning of our program is we would say something like count EQU 0x10, and then later on we can say increment file register count. And when the assembler sees count, it will go back and it will say, what's count? Oh yeah, count is 0x10. And it'll basically change this in its own mind to increment file register 0x10. Right, so this is what we would normally write, but we write this, it's easier to read. And then if we decide that count needs to go somewhere else in memory, we can just change this one statement. If we change this to 0x15, then increment file register count would become increment file register 15. So we basically set up a symbol for some magic location, and we call it whatever we want. Well, this is really useful when we're dealing with these special function registers. Because if we want to write something to latch A, we know we have to write to magic location F89. Wouldn't it be nice if somewhere in the beginning of our program we could do the following? We could say latch A is equivalent to 0x F89. And now we could say move W register into file register latch A. And internally it'll say, okay, I'm going to move the W register to location F89. But when we read this, it's really clear what's going on. Oh, we're taking the W register, we're sending it to latch A, right? So we'd like to have a bunch of these EQU statements that would basically set up symbols like port A, port B, latch A, tri-state B, and so on, and set them equal to these magic values. And then when we want to do something with these values, we can just use the name that we set to be equivalent to that magic location. But don't write a bunch of EQU statements yourself. That's too much work, and that's also error prone, and it's not portable from one processor type to another. So instead, you can add one statement in the very beginning of your program, which is include P18F1220.inc. And if you put that in the beginning of your program, it will automatically pull in another file that has a whole bunch of these EQU statements. And that's going to make your life a whole lot easier. So what's that going to look like? It's going to look something like this. Sorry, there's a number sign in front of include. So you're going to say include P18F1220.inc. You're going to put in your config statement. You're going to put in your org statement. And from that point on, if I say clearF tri-state A, that means the value that tri-state A was equivalent to, which in this case is the magic number F92. And we can use these things like latch A, addcon1, tri-state A, and so on, by these nice mnemonic names instead of hard coding magic numbers. Now some magic numbers like 7F we still have to code because that's a number, it's a literal that we want to copy to this. But we're going to avoid magic numbers for these file register locations. Okay, so you're going to want to do this number sign, include P18F1220 up in the beginning of your program, basically before you start trying to use these symbols like latch A and port B and so on. All right, that's enough to get you going on Lab 2 with one additional detail, which is the go-to statement. If you say go to some location, then instead of incrementing the program counter by 2 to go on to the next instruction, it will load the program counter with whatever this location is. And so the next instruction you execute will be the one at this location. So if I said something like go to 0, no matter where I am in my program, the next instruction that's going to be executed is the one at instruction memory location 0. If I say go to 6, the next instruction that will be executed is the one at memory location 6. All right, so how do we know what memory location we want to go to? Well, we can use a label. So again, if we look at some sample code, up here in the beginning of this statement, there's this word loop followed by a colon. That's a label. And later on, when we say go to loop, loop gets replaced by the address of the next instruction after this label loop. So this statement, go to loop, basically causes the PC to load the address of this instruction. So after the go to, the next instruction that's executed is this move FF. So this code is basically a loop. It gets down here and it goes back up to this move FF, move FX, or WF, and so on. So we can make things repeat, okay, and that's something we're going to have to do for Lab 2. Okay, so with that, that's enough to get you going on your lab. So we'll explore some of these things in homework questions.